Okay, I'm going over the review here today for Unit 6, Section 1. We have our quiz coming up this week. The quiz will be pretty short. There's only going to be 2 questions. One question that's like the first 3 on this review, and one question that's like the last 3 questions on this review. Let's jump in. So we're going to graph the linear programs, shade the feasible region, state the intersection points, and find the minimum and maximum value. So let's graph our constraints first. -7, or y value -7 is going to be down here. Y value -3 is going to go right here. X is greater than or equal to 0. That is a horizontal line here. And then x value is less than 5 right here. And if you want to try to figure out where to shade by looking at these, you can, but it's kind of obvious here what's being enclosed by all these lines. And then we got to find our intersection points. Looks like we got one at 0, -3, one at 5, -3, one at 5, -7, and one at 0, -7. All right, and now we got to find the minimum value. And remember, the way we do that is we plug in to our objective function. We plug in each of these things and see which one gives us the minimum and maximum value. And let's do, I guess we're doing maximum first. It's going to occur at 5, -3. If I plug in 5 and -3, and for x and y, I end up with 0, which happens to be the highest value we can get here. Our minimum value is going to occur at 0, -7. And I'm going to get something like -35 for that. All right, that's the first one. So let's do the second one here. I'm going to graph the constraints here. So x is less than or equal to 6. Oh, whoops. Y is less than or equal to 6. And then this is already a nice intercept form for us. So we have a y-intercept of 9, then we're going down 3 over 1, down 3 over 1. And if it's pretty obvious where our region is. All right, our intersection points. We have one at 1, 6. One over here at 6, 6. One down here at 6, -9. And then our maximum minimum, you'd want to plug each of them into your cost function to see which one works. Our maximum is going to occur at 6, 6, and you're going to get 67. And our minimum is going to occur at 6, -9, and that's going to give you a minimum value of -23. All right, let's flip over. If I go to number 3, I got to graph these. The x is greater than 0, the y is greater than 0. Those are easy. These are not nice right now. You need to put these into slope-intercept form. So I'll just quickly go over this first one here. I'll subtract over the 2x first. I'll divide by 3 to both sides. We're going to get -2 over 3x. And then 12 divided by 3 is 4. I'll do the x plus 3y is less than or equal to 9 next. And I'll subtract over the x. And I'll divide over the 3. And we get that. And if I'm going to graph this fellow first, it's got a y-intercept of 4. He's going down 2 over 3, down 2 over 3. And the other one, y-intercept of 3, and he's going down 1 over 3. So down 1 over 3, over 3, over 3. All right. So, this one you might want to double check, what the feasible region is here. Both of these lines are less than or equal to, so we'd want to shade below it. So for this line, we'd want to shade below, and for this line, we'd want to shade below. So it's going to end up being this guy right here. We have 4 intersection points right here. We got 0, 3, 3, 2, 6, 0, and 0, 0. And then you just plug each of these in to find your max and your min. The max is going to occur, I think, at 3, 2. Yeah, 3, 2. You're going to get 194, and the minimum is going to occur at 0, 0. That's going to give you 0. All right, so now let's get to the harder ones, the ones where you have to sort of make your equations. All right, so we got a factory making dolls and baseballs. Sure, it takes machine A 3 minutes to make a doll and 4 minutes to make a baseball. Machine A cannot run longer than 36 minutes in an hour. Machine B can make a doll in 3 minutes and a baseball in 1 minute and must run longer than 6 minutes every hour. The factory is not able to make more than 6 baseballs per hour. And then the factory cannot make a negative number of dolls or baseballs. That makes sense. And then we got some information about profit. Factory makes $14 profit for the dolls, $5 profit for the baseballs. How many of each toy must the factory make for a maximum hourly profit? Okay, so first assign your X and Y values. I'll let X be dolls and Y be baseballs, since that's what we're talking about here. Your objective function is typically going to have something to do with money, not always, but in this case, if you see profit, that's going to be your tip-off. That's going to go with your objective function. So our profit is going to be, we make $14 from every doll, so 14x, and we make $5 from every baseball, so 5y. So our profit is 14 times however many dolls we make plus 5 times however many baseballs we make. All right, our constraints are a little tricky to see here. All right, so machine A takes 3 minutes to make a doll and 4 minutes to make a baseball, and then it says machine A cannot run longer than 36 minutes in an hour. Okay, so every doll we make takes 3 minutes. So I'm going to say this. 3 times X, 3 times the amount of dolls that we're making, and 4 times Y, so plus 4 times Y, 4 times however many baseballs we're making. So however many of these we're making, we have to multiply the dolls by 3 minutes and the baseballs by 4 minutes. And machine A cannot run longer than 36 minutes in an hour, so that has to be less than 36. However many dolls and baseballs we make, if we're understanding the time constraints correctly, we have to multiply these together, and whatever we get has to be less than or equal to 36. We can't go over 36 minutes for some reason. Machine B, same deal. We make a doll in 3 minutes and a baseball in 1 minute, and this time we must run longer than 6 minutes every hour. So it's not saying we can only run as much as 6 minutes. We have to run at least 6 minutes. So I'm going to say this, 3x plus 1y is greater than or equal to 6. So we have to be greater than or equal to 6 minutes here. All right. So a couple other things. The factory is not able to make more than 6 baseballs an hour. So Y must be less than or equal to 6. What else? The factory cannot make a negative number of dolls and baseballs, and this is where we're doing the X is greater than or equal to 0 and the Y is greater than or equal to 0. And they will not always tell you that. If they didn't say that, we would need to assume this is true. You can't make a negative number of items. All right, so we have our 5 functions now. We need to graph these. I would want to put these two guys in slope-intercept form first. So if I subtract over the 3x, I get 4y is less than or equal to negative 3x plus 36. And if I divide over the 4, I get negative 3/4 x plus 9. For this guy, if I subtract over the 3x, I get negative 3x plus 6, and we're done right there. So if I graph these, this first guy going down 3 over 4, down 3 over 4, down 3 over 4. This guy, y-intercept of 6, down 3 over 1, down 3 over 1. And then the lines, the y is less than or equal to 6, so we're going to go through right here. Oh. and then x is greater than or equal to 0, and y is greater than or equal to 0. And there's a lot of possible regions here, so just look carefully. For this line right here, it had to be less than, so it has to be below it. For this line, it had to be greater than, so it had to be above it. So it's either this or this, and we'll use this line right here. Y is less than or equal to 6, so it has to be below this line. So this is our region right here. All right, our intersection points, 0, 6, 4, 6, 12, 0, and 2, 0. It's not asking for max and min here, it's just asking for our maximum hourly profit. So which of these points can we plug into this objective function and get the sort of the max value? And it's going to be at 12, 0. We're going to get $168. And 12, 0 basically means we're making $12 and no baseballs. So baseball is not a profitable item. All right. We had 2 more on here, so let's do these. All right, 2 workmen building chairs and tables. They make $30 profit on each chair and $40 profit on each table. That's probably going to be our objective function. The number of hours it takes each man to build a chair or table is below, so that's this table right here. The workmen can make no more than 12 chairs per week and no more than 6 tables per week. Okay, and Josh must work at least 12 hours a week, and Trey cannot work more than 18 hours a week. How many chairs and tables can be made per week to maximize our profit? All right, so we're talking about chairs and tables, so that's going to be our x and our y. Our objective function, use the profit for the tip-off. Our profit for each chair, we get $30, and for each table, we get $40. All right, let's do some of these easier constraints here first. The workman can make no more than 12 chairs per week, and so if chairs are x, x must be less than or equal to 12. No more than 6 tables a week, so y must be less than or equal to 6. All right, and now to use this confusing table. All right, it's giving us the hours to make a chair for Josh and Trey and the hours to make a table for Josh and Trey. And it tells us Josh must work at least 12 hours a week. So if it takes Josh 4 hours to make a chair and 2 hours to make a table, and he has to work at least 12 hours a week, we're going to set up a function that looks like this. 4 times x, so however many chairs we make, we have to multiply that by 4 for 4 hours, plus 2 times y, however many tables we make, we multiply that by 2 hours. And however many hours we spend making these furniture, we have to work at least 12 hours a week. So this has to be greater than or equal to 12. We have to be over 12 hours. We get that from there. Trey cannot work more than 18 hours a week, so he's going to be less than or equal to 18. And if we're looking at Trey, it takes him 1 hour to make a chair, so 1x, 3 hours to make a table, 3y. And he can't work more than 18 hours, so this has to be less than or equal to 18. We have 2 more spots, and there's no other information given to us. This is that thing where we just have to understand that we can't have negative chairs and tables. So x has to be greater than or equal to 0, and y has to be greater than or equal to 0. All right, let's graph this. 0, 0. I'll do these 2 easy ones first. X is less than or equal to 12, and y is less than or equal to 6. And then these guys we would need to get in order. He's going to be end up being y is less than or equal to negative 2x plus 6. He's going to end up being y is less than or equal to negative x over 3 plus 6. So if I graph this guy, y-intercept of 6 down 2 over 1. And the other one, y to the 6 down 1 over 3. Make sure we have the right region. This is greater than or equal to negative 2x plus 6, so everything above it. This one is less than, so everything below it. And so that's going to be this region. And our intersection points, we have 4 of them. They occur at 0, 6, 12, 2, 12, 0, and 3, 0. And our maximum value is going to be at 12, 2. Whoops. And at 12, 2, we have $440. Our number of chairs then would be 12 chairs and 2 tables. All right, last one. Carlos makes 2 types of wood clocks to sell. It takes him 2 hours to assemble a pine clock, which requires 1 ounce of varnish. And it takes 2 hours to assemble an oak clock, which takes 4 ounces of varnish. Carlos has 16 hours of varnish in stock and can work 20 hours. He makes $3 profit. All right, we got our profit. That's going to be our objective function. So $3 profit for a pine clock, $4 for an oak clock. How many of each type should he make to maximize his profits? All right, so we're talking about clocks here, and specifically we apparently have pine clocks. And we got oak clocks. Our objective function is going to have something to do with the profit. We're going to say profit is equal to 3 times our amount of pine clocks plus 4 times our amount of oak clocks. All right, our constraints. We are talking about, so what information is it's telling us how long it takes him to assemble a clock for each of these. So 2 hours to assemble a pine clock, 2 hours to assemble an oak clock, and he can work up to 20 hours. So however many pine clocks we make, we have to multiply that by 2 in terms of time. So each pine clock takes 2 hours. Each oak clock also takes 2 hours. And we know that however much time we spend making, pine clocks or oak clocks, that we have to come in less than or equal to 20 because we can work up to 20 hours. All right, so the varnish. We have the pine clocks take 1 ounce of varnish, the oak clocks take 4 ounces of varnish, and we have 16 ounces of varnish total. So 1 ounce of varnish for every for every pine clock, plus 4 ounces of varnish for every oak clock, and we have to come in under 16. All right, and then our last 2 constraints, it doesn't say anything else. This is that thing where you need to know that you cannot have negative items. So we have to have at least 0 oak clocks and pine clocks. All right, let's graph these. We need to fix this first. This guy is going to end up going to y is less than or equal to negative x over 4 plus 4. Do I have that right? No. That's this guy. My bad. Y is less than or equal to negative x over 4 plus 4. This guy, whoops, he goes to y is less than or equal to negative x plus 10. All right, if I graph these, so 10 down 1 over 1. And then this guy, 4, down 1 over 4, down 1 over 4. And then the x is greater than or equal to 0, y is greater than or equal to 0. This is going to be our region. You'd want to double check, but this is less than, so underneath both of these lines. All right, our intersection points occur at 0, 5, 0, 0, 10, 0, and 8, 2. Maximum weekly profit, it's either going to be the 10, 0 or the 8, 2. It ends up being at 8, 2. I plug 8 in for X and 2 in for Y, we get our maximum profit of 32. So our number of pine clocks was X, and we have 8 of those, and our number of oak clocks is Y. We have 2 of those. All right, that is it for the review. Please email me if you have any questions.